Hello, and welcome to the Redis Enterprise Session Management and Data Caching Virtual Workshop. We appreciate your time today and look forward to a great discussion. Please use the Q&A tab to submit questions or type them into the chat. We also have a few polling questions to understand where each of you is on your Redis journey. We will send out a recording of today's session together with additional resources next week. And now I would like to introduce today's speakers. Julian Rouault, Principal Field Engineer at Redis, and Tom Solon, our Professional Services Training Engineer at Redis. And now I would like to keep our session interactive and launch our first poll question. So this will be helpful to our presenters to understand where each of you is on your Redis journey. Some of you maybe haven't used Redis before at all. Others of you might be just starting out on your Redis journey. Others of you may be intermediate, and some of you might be quite advanced in leveraging Redis. So this just helps our presenters understand where each of you is on your journey. So we appreciate your responses. And it looks like we have about 40% of you who are beginning and just really starting out or completely new to Redis. And the remainder of you, about 30%, are intermediate, and the remainder of you are advanced users. So a very nice mix indeed of everyone across all parts of the Redis journey. So thank you so much for responding. I am going to launch our next poll question. And that is really to get a sense of which caching solution or solutions you're currently using in your organization. Some of you might be using Redis Enterprise. Others might be using Amazon Elastic Cache or Redis Open Source, maybe Google Cloud Memory Store or Azure Cache for Redis, or something completely different. So this just gives our presenters an idea of the portfolio of caching solutions that you all are leveraging today. And we realize that some of you might be leveraging multiple solutions. I know organizations and companies are quite complex. And so thank you all so much for responding. We appreciate that. So I'll give everyone just a moment to respond. It's a very nice mix across Redis Enterprise, some open source, and a portfolio of other caching solutions. So thank you all. And our third polling question now is in regards to which cloud provider or providers are you using? Redis is available across all of the cloud solution providers in their marketplaces, and you can also run Redis on-prem as well. So this just gives us a sense of where each of you is running Redis. And some of you might be running Redis on a portfolio of different cloud providers and on-prem as well. So this just gives our presenters a nice idea of how you have Redis deployed across your organizations. So wonderful. I will end our poll there. And now, Tom, I will hand things over to you and Julian for our workshop today. Thank you all.
All right, excellent. And welcome to Redis Enterprise for session management and data caching. Here's our agenda for today. We're going to start out talking a little bit about Redis as a session store, then Redis as a cache, and then some of the application implications of those things, including the data structures and which ones are more suitable towards session storage or caching. We'll get into Redis JSON and Redis search, and again, how they apply to the topic at hand. And then Julian's going to give a really cool demonstration of Smart Cache, which is out of the box that you almost plug and play. I'll let him describe it. So Redis is a session store. Let's start at the very beginning. It's a very good place to start. HTTP is stateless. Enough said. So One of your options then for stateful sessions is to store the session information server side. You can use one of the off-the-shelf frameworks to manage your session data if they meet your needs, but there are, of course, always trade-offs. Now, if you choose the route of storing session data server side, then whatever method you use to store the session data, you would use one of these three methods to identify returning users to match them with that data. Either cookies in the header, URL rewriting in the URL, or a hidden form field in the body. Now, for a cookie, that would go something like this. The server includes the set cookie header. Then when the user goes to another page on the website or submits any request for that matter, the browser includes the cookie in the header. Of course, there are practical limits to what you want to store in a cookie. You should not store a lot of information or any sensitive information in cookies because they're not trusted since they can be modified by the client code. You also need to manage session expiration. How long a session stays alive depends on the use case. Short for banking, long for social media, and somewhere in between for e-commerce. The initial interaction with the server is typically anonymous. After the user authenticates, the server issues a new session ID, all right, which can then be used rather than logging in again on every request. The important point here is that only the session ID is stored client-side. The session information itself is server-side. Another option, though, is to use a token, which will be returned in the authorization header. In this case, the server doesn't necessarily have to store the session data because it can be encrypted into the token. This table summarizes the difference between using a token and passing a session ID in a cookie. The bottom line is the bottom line of this table, that is. Tokens are typically used in apps and session ID commonly used for websites. Of course, that's not a technical requirement, just a common use case. And they're not mutually exclusive. You can use both. The most obvious example being, an OAuth login to a website, but still using server-side session management. Now, going forward will be the session-based approach since, well, like the name of this workshop says, session storage and cache management, right? Which brings us to this dilemma. Since the session information is stored server-side, what server, right? When you have multiple app servers behind a load balancer, subsequent requests may go to a server that doesn't have the data. One option is for the load balancer to track who serviced the original request and then always route subsequent requests to the same server. This is also known as sticky sessions. But that has its own challenges, not the least of which is what happens if the app server goes down. So if the app server goes down, you lose the session information. If the load balancer goes down, you lose the connection to the session information. Either way, you're not in a good position. Also, if there are multiple services on separate app servers and they need to share data, then it's not good enough to have it on just one server. And then there's the additional complication of what if you're running in a containerized deployment? Enter the database. All right, to solve these and other issues, a centralized database is often used to store the session information. And I'm here to tell you that Redis has the key features needed to fit that use case. Both reads and writes need to be extremely fast because sessions need to be updated frequently. Redis does that. Also, the session data needs to be highly available and in some use cases may need to be persisted. Redis does both of those. Now you may be asking, isn't session store just another type of cache? No. Short answer, no. They serve complementary objectives. That's why we have them in the same workshop, but they're not the same thing. All right, sessions are unique to a user or client, while cache data is typically global to an application. Cache data can be lost and then rebuilt from the source database, while session is active data and Redis is the source of truth. All right, sessions have state that gets updated over time. Cache, of course, only exists in the latest state. Sessions have additional requirements to ensure that state is not lost. For example, high availability and persistence. This table shows just a few of the session data that you may need to store, as well as the features likely to be needed for that particular use case. Here, TTL, of course, is time to live, and HA is high availability. You wouldn't want to do anything halfway. We'll talk about these and other data structures when we get deeper into the development aspect. But these are the structures that obviously lend themselves to session storage. Each has advantages and disadvantages. Strings are simple and easy to use, but cannot be automatically indexed for search. The hash structure is an obvious choice for field value pairs that are common in session data, but they can't have nested objects. JSON handles field value pairs, but can also take objects and arrays as values. But JSON documents take a little more space than hash. Now, both hash and JSON are automatically indexed if you're using Redis search. There are other Redis data structures that are suitable for specific use cases, as long as you remember that the data needs to be indexed to achieve real-time performance. Also, of course, there's nothing to prevent us from writing bad code. Hashes and JSON support lazy loading, getting only the data you actually need at a particular moment. But neither forces you to do that. If you constantly get the entire session, well, it won't end well. So then, what factors do you need to consider if you're going to create your own Redis session data manager? These are the two general areas you need to consider. First, what capabilities do you need to provide? Here we need to consider things like a TTL that can be updated, lazy loading, leveraging core data structures, and ease of search. Second, you also need to consider what sort of data you'll be storing. It will likely include these: key value pairs, objects, collections, and geographic locations. You know, like when you get that alert, xyz.com would like to track your location, allow or block. When it comes to adding key value pairs to the session, both hash and JSON data structures are a good fit in Redis. Objects also lend themselves to be stored as hash or JSON. The added value here is that Redis search can index any nested field and perform powerful cross-session searches. For collections, you can use the standard collection structures, right? Lists, sets, sorted sets, and so on. But Redis search doesn't index these. But if you store your collection as an array within JSON, it can be automatically indexed. And we'll get to the syntax for that later. So using JSON full text search can be done on arrays of strings, numbers, or geolocations, or you can also search on a JSON path that leads to multiple strings, numbers, or locations. It's also important to only load the information you're actually going to use, not all the data in the entire session object, right? JSON gives you that ability. So does hash, but I'm starting to get fond of JSON here, so that's why I'm using it as an example. So these are the requirements for a session manager. It must use the fewest structures so that TTL can be updated easily, provide robust indexing, provide for searching both within and across sessions, and use low complexity queries. The natural choice for these needs is Redis JSON. We'll take an in-depth look at Redis JSON in a little while. But first, let's consider the related topic of cache. All right, distributed systems require low latency and scalability, right? The challenges of disk-based database, they are slow, expensive, and complicated. Benefits of adding Redis as a cache, it's fast, high volume, easy, and efficient. Applications use cache to store common, repeatedly read objects. Here are a few examples of candidates for caching. Objects, simple key value string pairs, native data structures, or even entire files. Now, data eviction policy is important in caching situations. To get the most out of your cache, it is common to run at or near capacity. So then what happens when your cache hits the limit? Well, let me put it this way. What happens when you run out of memory? You forget things, right? Except here, you get to decide what the database forgets. One of the options is no eviction. So that's kind of like, when you walk into a room and can't remember why you went there in the first place. Your brain just threw an out of memory error. All right, the most recent write was not accepted. Other than that, there are two general options. All keys, which, surprise, surprise, will look at all of the keys when determining what to forget, or volatile, where volatile is defined as a key that has an expiration set. In other words, you as a developer have already flagged this piece of data as something that's going to expire eventually. And so we will preferentially consider those for forgetting, for evicting from the database. Then within those two categories, you have the choices of least recently used, least frequently used, or random. Volatile also gives you one more option, volatile TTL. That's going to evict the shortest TTL from amongst the least recently used keys from amongst the keys that have an expiration, which is kind of redundant because, of course, it wouldn't have a TTL if it didn't have an expiration, but you get the point. So by choosing your data eviction policy well, you can control the efficiency of your cache. The next decision is how to manage the cache. For this, we'll look at some of the common design patterns for caching applications, starting with the very common look-aside pattern, also sometimes called cache-aside. Here, all write operations go directly to the slow database. Reads first look in the cache, and then, only if it's not found in the cache, a second request goes to the slow DB, followed by a write to the cache. A big advantage is that the cache doesn't need to hold a copy of all the data. A big disadvantage is all the extra work on a cache miss. With write-through, all write operations are synchronously sent to both the fast Redis cache and the slow disk database. Then all reads go exclusively to the cache, which will always be in sync. The downside is that you have to first load all the data into the cache. And besides that, every write happens twice. Now, this one is a twist on the traditional write-through that makes use of another enterprise feature, Redis Gears. This simplifies the application code, which then only reads from and writes to the Redis database. Behind the scenes, Redis Gears writes to the backend. Other than the simpler app code, this has the same advantages and disadvantages of any write-through mechanism. By the way, Redis Gears RG Sync has a built-in recipe enabling write-through. The follow-up email after this workshop will include a link to the GitHub repo for RG Sync, including some sample code for implementing it. Along a similar vein is write behind. The difference is that writing to the slow backend is asynchronous. The example on the screen also uses Redis Gears, this time adding a stream as an intermediate step to facilitate the asynchronous replication to the backend. RG write behind is also a Gears recipe in the RG Sync repo. So we talked about write through. It shouldn't surprise you, there's also a read through. Here, the writes go to the backend database and reads go to the cache, like look aside. But on a cache miss, the application doesn't need to make an additional request. Redis retrieves the data from the backend and returns it while storing it in its own cache, of course, for the future. Last but not least is change data capture cache replication. Here, only the reads go to the cache. Writes go to the back end, while a separate CDC process replicates the changes to the cache. So now let's talk about what that means to you as developers. Redis data structures use unique layouts and operations for storing and accessing data efficiently, often in milliseconds or sub-milliseconds, even for enormous data sets. The key benefit is the simplicity. Our data structures mirror your programming data structures, the same ones you learned back in school. All right, no schemas to worry about. Also means no free-form searches like relational database, and no automatic secondary indexing. There's no such thing as a foreign key, at least in the literal technical sense. But the benefit is reduces impedance. It reduces all that extra work that you need to put into it to change your sets and lists and hashes or hash maps or dictionaries, whatever your language calls them, into rows in a database table. So each data item consists of a unique key and an associated value. But those associated values can be of any of the supported data types. The box is shown here. A hash is kind of like a hash map of key value fields. And a set is, well, a set. This is showing you an example of using hinkrby to increment the number of visits in a particular session. So hypothetically, the key is the session ID. And when Johnny Rambo comes back to this page or to this site or whatever, makes another request, we simply increment the single value for visits rather than having to retrieve the entire hash and then update one value and put it back. So why are these data structures useful? In-memory data structures are fast and compact, for starters, which means Redis can be used as a database, a cache, a message broker, session store, queues, stacks, time series data, geospatial data, and we support search. So let's talk about some of the typical use cases. Now, previously we said that string was not an ideal choice for session storage. But caching is a different use case, one that may be well suited to strings. For example, using a string to cache a web page. All right, the typical web page is an HTML document, which is essentially a big long string. Now, shown here is a separate expire command. because of course, when you're caching web pages, you do need an expiration, but you don't have to do it as a separate command. You can use the expire arguments, ex, and then a number of seconds, or ex at, and a timestamp, so that you could specify that right at the same time that you're doing the set. The lower box here is simply showing the same commands in a supported Java library. If you're not a Java programmer, don't panic. That's the last Java we're going to be throwing at you. Well, we don't throw our Java around here. As previously discussed, there are reasons that you might want to use JSON rather than hashes, but that depends on your specific needs. Let's look at the hash option. All right. Why is it a good fit? Well, hashes are already built for these field value pairs, kind of like a Python dictionary. You can set variables, either the entire thing with hset or individual fields. You can get multiple fields. You can increment or delete individual fields. So it could look something like this, where we've got our initial session, user session 1, user ID, whatever, name, Dave, IP address, hits 1. If you need to get specific fields, HMGet will allow you to do that. All right, in this example, I'm actually getting all of them. That's not a very efficient way of doing things, but let's say we only need the user ID and name. We could do an HMGet for user ID and name. We need to increment the number of hits. We do hinker by user session 1, hits 1, and we increment it by 1. You need more data. We're schemaless, no problem. We can do that. Simply do a hset, key name, last page, home. And then you need to see what his last page was, hget. Dave was last on homepage. You don't need that information anymore. You can do an hdel and delete just that one row. The Dave logs out. I mean, you could wait for the expiration, but typically if the user explicitly logs out, we're going to delete the session. And you can use del and the key name to do that. We'll look at the JSON use case later. Got a whole presentation just on the JSON. Now, queuing. You can use Redis as a queue. For example, you've got tasks that need to be processed asynchronously. You want to assign items to worker processes and remove them from the source queue at the same time. Maybe it's kind of like you've got a microservices architecture, and it's not exactly caching, but you can think of it kind of on the idea of caching request and response. You can use lpush and rpush to push things onto the queue, and lmove, or well, I mean, lpop or rpop, of course, to pull them, pop them off, but lmove will actually, in a single transaction, pop it off of one queue and push it onto another. So Redis has a lot of uses in building microservices-based architectures. And in fact, we're going to have another virtual workshop coming up specifically on that. But one of the most common use cases is as an asynchronous communications channel. So Redis can implement a high-speed queue for sending commands, responses, and other data asynchronously between neighboring services. That's what's shown here, where service A is set up to send messages to service B using the Redis list object within your Redis instance. Another queue could be set up for the reverse trip, where service B pushes its response onto a queue where it awaits consumption by either service A or some other service entirely. So requests can be added to a queue and then popped by another process, or even just moved to a processing queue. So here we're saying, for example, we're pushing first an orange job, a green job, a blue job. Then we get a high priority job, red. And so we push it onto the front end of the queue. which is technically the tail of the queue, but never mind that. The point being here that when it comes time to service that request, we can simply list move it from Q1 to Q2 and specify that we want to pop it off the right and push it onto the left, or any other combination of directions that you need. Another thing you could do is for keeping track of requests, for example, managing your cache. Has this operation been requested before? If it has, then the response should be in cache. Otherwise, we'll add it. This could also be used for recommending similar purchases or similar blog posts or similar whatever, or identifying fraud. All right, so sets are collections of unique strings that is great for quickly determining membership. sadd adds a request to a set. So this is not a depressed set. It's not sad. It's sadd, as in set add. You want to find out if a request was already made. S is members. You want to get all the members of the set. S members. Find similar sessions with the same tags or same commands used. S inter to get an intersection. And this gives you you could sort of think of this like a manual secondary index of who has issued what commands. We'll talk about sorted sets next, but that could be used as an enhancement on this idea by giving each entry a score that's the timestamp of the request. So for example, I've got command 1 and I'm keeping track specifically of the IP addresses that have issued this command. And so these get added as the requests come in. You want to find out, okay, which ones? Here it is. You may notice that 10.3.1.12 is only listed once in S members. That's because of the nature of a set. It is unique items. So even though they've made the request twice, it's in the set once, because that's all we really need to know about it anyway. They have made this request. Did this client invoke command 1 before? S is member, the key, and then the value. And in this case, it comes back 1, where 1 means true, and if it were false, it would return nil or null. Now, let's say you want to tag sessions according to some business criteria. You could create a set for each tag and then sadd members to it. Then you can find all the sessions with a particular tag. If you write your code carefully, you can also get intersections and unions of the tag. In a little while, I will explain what I mean by write your code carefully. Some of the common commands: sinter for intersections, sunion for unions, sdiff for differences. Here, I've made the hypothetical argument that there are different processing paths for business accounts than personal accounts, and perhaps different processing depending on whether something has an item in the cart. Probably not a really good example, since items in the cart, there are other ways of testing that, but sets, let's face it, that's going to be quicker than searching all the carts, right? So here I want, hypothetically, an intersection of business accounts that have something in the cart. Here it's a business account, or it has something in the cart. And here are example of carts that are not business accounts. Redis is a leaderboard score. Again, talking about caching, maybe this is, maybe this isn't something important to you. On the other hand, if you're looking at this as you've got this huge, slow backend database for your massive multiplayer online gaming app, and you need a fast leaderboard score, you might think of this as kind of a caching situation. Technically, it's actually a different storage option for sorted sets. Now, S was already taken for set, so instead we're using Z or Z, depending where you are. We have quite a few people here from Canada, so you would Z add to update or add a new item to the sorted set. Z range gets you the ascending list of values. Z rev range, as in reverse range, gets you the descending values. Z rank gets you the rank of an individual value. And so that might look something like this. You've got these players entering the game with their starting scores. Then player 3 breaks a vase and finds a gem and gets 10,000 points. Z Inkerby for game 1 for user 3, 10,000 points, not only adds the points to the score, but automatically resorts the set so that user 3 is now in position 0. You want to find out who's the leader? Z rev range, rev because you want it descending. Game 1, 0, 0, the 0 through 0th item. And that is user 3. You want to find out the top 2, 0, 1 instead of 0, 0. You want to know their scores too? Include the argument with scores. Pretty straightforward. You could also use Redis for geolocation. Give me all the pharmacies within a 2-kilometer radius of the user, or which sessions are near this warehouse, or which store is closest to that user, or where are the apps connected to this service. GeoSet does that. So now we've given up on the idea of single letters. We're just going to go ahead and do a GeoAdd, GeoDist to get the distance between 2 items in the set, GeoRadius to calculate which items are within a particular radius, or GeoSearch if you want to search instead of by radius, by box. All right, and the reason, by the way, that I referred to this as a set, besides that its name is GeoSet, is a GeoSet is actually a specific use case of the sorted set. And so that could look something like this, where you initially load your data, in this example, pharmacies in London. And then when your user says, hey, I want to know the pharmacies within 600 meters of my current location, you would write your code like this. Or maybe the user just says near me, and you have predefined that the default for near me is 600 meters. I don't know, whatever. The point is we feed in the user's longitude and latitude, the distance, the units of the distance, and of course, they're not just interested in the name of the pharmacy. They want to know how far is it and where is it. And so we also say with dist, with coord, ascending. And we find out that the only pharmacy within 600 meters of that location is the Charles Harry Pharmacy, which is 511.7 meters away, and at these coordinates, which you can then feed in to your mapping app to drop a pin on the location. Another option for inter-service communication is PubSub. Now, PubSub does have its limitations. This is a way of sending a service to multiple notifications, such as sending out app messages to activities to multiple users. But the only users you care about are the ones that are currently using, right? If you need to have a reliable, persisted message, then you probably want to use streams or a queue like we showed before. So PubSub broadcasts messages to subscribed listeners. The idea here is that clients subscribe to and receive messages from channels. rather than individual publishers. And the publishers publish to those channels rather than sending messages to individual clients. Multiple publishers can send to the same channel. Multiple subscribers can be subscribed to the same channel, or vice versa. A publisher can publish to multiple channels. A subscriber can subscribe to multiple channels. So those are the basic data types. Now, it gets a little complicated if you're looking at wanting to cache or store sessions for apps that have lots of users. You're probably going to be needing a sharded database. Basically, if you need more than 25 gigabytes of data, or you need to service more than 25,000 operations per second, you need to shard. The way we shard is through hash slots. So we have a hashing algorithm, a basic CRC16 modulo 16K will get us a number, an integer, between 0 and 1 less than 16K. And then those will be equally distributed amongst the number of shards. So in this example, we're showing that we have 4 shards. And so each of those shards will have 4K of the hash slots. The hash slot will have the key value pairs determined by running the hashing algorithm on the key itself. So for example, I've got users for user ID, events for user ID, messages for user ID. We're going to perform the hash on the key, and those are going to end up in slots. Now, before I go further on that, let me talk about some of the conventions that you probably, if you've used, those of you that have used Redis before, understand the basic idea with the importance of keys. If you're new to Redis, it's important that you realize, this isn't a relational database. So the relationships aren't stored in rows in a table. But that doesn't mean you can't express relationships. Here, we're using the key itself to express relationships. All right, so the relationship of item 101 is a math course, or 11 is a pending task. You can even show multiple relationships. So for example, student 1 is in many classes. So student : 1 : class 1, 2, 3, and student : 1 : class 4, 5, 6. Now, the issue is that multi-key operations require that all of the keys be in the same hash slot. They be in the same shard, but also the same slot. So multi-key commands like those unions and intersections I talked about before. lmove, another example. Also transactions. We'll look at an example in a little while, but a multi-exec with a watch or without a watch, anything in that entire transaction has to be in the same hash slot. Lua scripts, if you're using those as kind of like a stored procedure, everything in the script got to be in the same hash slot. So what are you to do as a developer? Well, one of the things you can do is use Redis Enterprise. The data management controller proxy helps with some commands, but as you see on this list, not a whole lot. The other thing you can do is co-locate keys using hashtags. All right, so here, the similar example to what I showed you a couple slides ago, but now I've added curly braces, not shemp braces, curly braces. All right, users : curly brace, user ID curly brace, events : user ID in curly braces, message colon, user ID in curly braces. What these hashtags do is say, only put what is inside the curly braces into the hash algorithm. Therefore, since all of these keys have only the user ID in the hashtag, and therefore only the user ID in the hash calculation, they'll end up in the same place. Here's that multi-exec example I told you about. So let's say we want in a single transaction, that's what multi-exec is going to do for you. You want to xadd is streams, X for streams, because S is overused. So xadd will add a stream events colon user colon 555. So user 555 has had an event. The asterisk says include the server timestamp as the tracer for this event, if you will. And then the type is alert on sensor 4. You also at the same time want to set a message for that user, check alert sensor 4. And you want to hset their session to say user 555, your status is attention needed. Because of the hashtags, all of those, the calculation will be on 555. All right. So if you want to have an impact on the hashing algorithm, you use these curly braces. Brace for impact. So now let's take a look. I've promised you that we'd get deeper into JSON. Now it's time. Redis JSON is a Redis module implementing the full JSON standard. So ECMA 404, JSON data interchange standard. I actually could find that. All right. So it includes JSON path-like syntax for selecting elements inside documents. We'll see why that's especially important to us in a little while. The documents get stored as binary data in the tree structure, which is going to allow you fast access to the sub-elements and typed atomic operations for any JSON value types. So how can you store JSON? Could you store JSON before Redis JSON? Well, sure you could. You could use string, you could serialize them into strings, or you could decompose it into a hash. But each of those have downsides. The biggest value adds of Redis JSON are these: atomic operations on values, no extra memory or network bandwidth, serializing and deserializing and so on. Nested JSON is supported, and multiple data types are supported, specifically any data type supported by ECMA 404. All right. Now, this is the JSON we're going to be using in the examples and the rest of these slides. When I get to the demo in a little bit, it's going to be a little bit more complicated, but for now, this will do. So you use JSON set to set the value. Like hset and set, if this key already exists, we will update the values. If that key doesn't exist, we will insert this into the Redis database as a new key value pair. Then to get the whole document, just JSON get and the key. Or if you wanted to, you could also specify the path, root. To get a particular property of the document, it's simply the path to that property. In this example, root.last access time. To get an item in an array, $.visited, square brackets, 0. And that will get you the 0th item in the visited array. You want to know the item ID for the 0th item in the cart? Cart bracket 0 dot item ID. Now it supports JSON path syntax. So if you had wanted all of the item IDs, so the item IDs for everything in the cart array, all you'd need to do is put an asterisk in place of the 0. And that says, get me all of the items in the cart array and return their item ID. To append to an array, so you've got this visited array of pages visited and you want to add another page in your website, JSON append, as in array append. You need to increase a number. They want an additional 2 widgets, whatever cart item 1 is. JSON num increby. You want to know all of the keys at a specified path or level, JSON obj keys, as in object keys. So let's go on to, I've got a quick demo here. This is the JSON that we're going to be using, or an example of it. So we've got last access time and creation time, which are numbers. User, which is an object that has name and last. Authenticated, which is a Boolean. Visited, which is an array of strings. Location, which is a string that has a geo value in it. Cart, which is an array of objects. And within the objects are strings, actually tags. We're going to decide to make this, but it's in JSON, it's a string. Number. So let me switch over here now to my demo environment. The demo environment is just my free Redis Cloud database. And it's not free because I'm an employee. You can get one free too. And this is Redis Insight connected to it. So I only have 4 sessions here just to keep it simple. And so I didn't have to use my imagination too much to come up with a bunch of different sessions. And so here's the Paul Bunyan example that we saw in the PowerPoint. And of course, there are other things also going on in this. So let's say I want to add a new session, and that would be with a JSON set. Now, there are a couple of different ways in Redis Insight to do command line. I could actually bring up the command line tool, but I've decided here to use the workbench because that's going to actually show me then a history of everything I've done. So I'm going to make a new session and say, okay, last access time and creation time are the same, or apparently 1 millisecond separation between the two. Authenticated true, name, John Doe, the pages they visited, their location, and the items in their cart. And so that's okay. We've added this session object. All right. To get it, let's say I want the location. I could do that and see, so John Doe is at Navy Pier in Chicago. I want their entire cart. I can do that. And so here they've got an HP 2341 and a MacBook. Let's say I only am interested in the MacBook, but I don't know which line item it is in the cart. I can do this. So this is a glob, a regular expression kind of thing. It's part of JSON path. This is not doing a search technically, or at least it's not a Redis search. This is saying, go to the cart and get me the item ID. So in other words, fill in this wildcard. Get me not just the item ID, excuse me, but get me the object that has an item ID of MacBook. And so that will find, so to speak, that object that meets that criteria. If I need to get the last access time, that can be done like this. If, John Doe does something else and I want to update the last access time, I can use a JSON set, and that will update only that one value without messing up anything else. All of the rest of the data, the cart, for example, is still, got to click the arrow for that, is still there. But now let's talk about search. So Redis search, source available search engine for querying, indexing, and full text search. Why is it important in this discussion? Well, like we discussed, if this is going to be a real-time session store, you're going to need to be able to quickly, very quickly, search the sessions for the appropriate information or even finding the right session. Redis search can query numeric ranges, tags, we'll talk more about that in a moment, geo queries, do aggregations. We can do full text search. You can rank the documents. Built in is text frequency, inverse document frequency, but you can also give scores to the documents themselves or weight individual fields. What this allows you to do, that doesn't change whether you get a hit or not. That changes the sorting of the results that come back from the hits. You could also use it for autocomplete suggestions, including fuzzy prefix suggestions, spell checking based on dictionaries or known words in a full text index. All right. You can also do complex Boolean queries, ands, ors, nots, and so on. So the idea is we create an index. The index is a collection of documents, each of which has a document ID. The documents have multiple fields. The documents don't have to have all the same fields. Here, document 2 has color, but document 1 doesn't. No problem. The documents themselves are schemaless. Not all the fields are relevant in a search, so you don't have to index all the fields. And in fact, you should not index all the fields. That's a whole lot of extra overhead. That would be like indexing every column in your relational database. Doesn't end well. So the index structure itself is defined by a schema. The schema is for the index, I want to emphasize, not the document. The schema defines how the fields are stored and indexed. Ever since Redis Search 2.0, there's no extra work required. When you create an index, all of the existing documents that meet the criteria will be indexed. Every time you add a new document, it will be added to the index if it meets the criteria. So here's a very simple example of a schema for a hash index. In this case, e-commerce products. That same one now shown as a schema for JSON, where we have the JSON path syntax, and with JSON, you can assign an alias. This is going to be especially useful if you've got a rather lengthy JSON path to the item. Now you can shorten that all by just saying, yeah, we're going to call this color, or we're going to call this price, or whatever. And that brings us back to our earlier discussion about how to store session data. I'm not going to go through this slide again. This is just the kind of the tie-in. I'm going to get to the next. There we go. I had to click exactly the right place. Sorry. So creating a search schema always starts with modeling the data to be searched. So we're going to start with this assumption that we have this general type of data. In other words, this is what I'm expecting for my session. So for that, we might do that something like this. FT create is the syntax to create an index. I give it a name. I specify the type of data. The options are hash or JSON. And then I specify the prefix. So any key that starts with session : is going to be included in, if it's a JSON, it will be included in this index. If it's a string, it won't be in the index. It won't break the index either. It just won't be included. All right. If I had multiple, like session A, session B, session C, I would simply say, okay, my prefix is two things, session and session X or whatever. I just specify my prefixes. And then the schema. So I want last access time as last access time. It's numeric and I want it to be sortable. By declaring an item sortable, that makes it quicker and easier to get your results in sorted order. Creation time, also numeric sortable. Visited as plain text. Cart star.item ID as item ID, and I'm saying that's a tag. Now, first, let me explain the syntax. This is why I gave you that example on the earlier slide. This is the syntax that says, get the item ID from any object in the cart and index that under the simplified name item ID. By specifying tag, I'm saying I want these values are as is. Presumably item ID is, like a predefined identifier in a catalog. And so you're not going to stem that. There aren't going to be multiple versions of it. It's a concrete item. Think of it kind of like a set of strings. Not an enum of strings that's a finite number, but a set that you can add more things to as they show up. Location, $.location as location, which is a geo. So even though JSON only knows it's a string, because ECMA 404 doesn't support geo, but we're saying to this index, hey, that string is going to be a geolocation. And then $.user.last as name. And it doesn't matter that there's also a $.user.name, which has the first name in it. This is just the alias for user.last. It's going to be text and no stemming. Presumably, at least in the English language, you don't have past tense or plural of your last name. So to add a document, it would look something like this. This is something we've seen before. So there's just adding the John Doe. Before I go on, just the field types. These are your options you have in your schema. Number fields, vector quantities. So this would be floating point vectors that you got from your external machine learning model so that you can do vector similarity searches. Geo fields, like I just described. Tag fields, and here's the additional information about a tag field. Or text fields, which are going to get tokenized, can be weighted, can be sortable. Tags aren't sortable. And they're always going to be, by the way, transformed to lowercase. In other words, the net effect will be a case insensitive search. So every time you modify a document, if you modify an indexed field, the index gets updated automatically. If you delete or add a document, the index automatically gets updated. It's asynchronous, by the way, but it will get updated. So that's creating the FT create and how it's going to work for you. Now let's talk about querying. Querying is ft.search you specify the index name, and then field : value. So for example, @name : Doe. For numeric fields, you include the values in brackets. So for example, FT search on session index, last access time between this timestamp and infinity and beyond. So plus inf is actually a special character that means unbounded upper end. So in other words, anything since that date timestamp. Here's the syntax for various other variations of redundancy. Anyway, of numeric values. So inclusive, partially inclusive, no upper range, no lower range, and so on. Equality, inequality. On tagged fields, it's @ field name, and then you include the value within these curly braces, and they are necessary. So for example, in John Doe has a MacBook. If we didn't include these curly braces, this would not find it, because MacBook is not text, it's tag. And if we didn't include the curly braces, that would be saying do a text search on this field. That's the point. For geolocations, it is once again using the brackets, the longitude, latitude, and then the radius and units, where this is an exhaustive list of the units available to you: meter, kilometer, mile, or foot. Obligatory, those exact abbreviations. You may be thinking, well, why isn't it lat long? Well, because Salvatore Sanfilippo was a programmer, not a map maker. And longitude is the X coordinate and latitude is the Y. And so basically use that to remember what you need to put in for your geo searches. It's XY, not YX. Full text searches. Simply do not specify a field. And then this, for example, FT search for www.redis.com is going to search any text field, not tags, not numbers, text fields for that value. And logic. You will notice that there is just a space between these two items. That means and. So in other words, by default, space delimited means and. So this is saying, get me the value, get me the object that has item ID MacBook and last access time since this timestamp. Or get me the sessions that sessions that have redis.com and visited redis.io. If you want it to be or, you use the pipe or bar or whatever you call it. All right, the or symbol is what I call it from my Java background. So now instead of and, we have MacBook or last access time, HP 1234 or Canon 5678, visited redis.com or redis.io. To negate your search criteria, you use the negative sign. Pretty intuitive, right? So negative @ field name : val1 says, get me the sessions that don't have a MacBook. With plain text search, you could do negative quote redis.com space negative quote google.com, or put them all within the same quotes So this means this does not mean, let me put it this way, this does not mean I'm looking for an address that starts with a hyphen. This says I'm looking for Redis is in the text, but Google is not. Last but not least, if I need an exact match, then I need to include it in quotes. And then I need to escape those inner quotes, lest otherwise the parser think, quote, quote, okay, we're done. You're looking for nothing. No, quote, escape quote, bright space star, quote, escape quote, close quote for the request. One last thing before I get to the demo for this. Open source, you're searching one shard at a time. With Enterprise, you are searching the entire database because we make use of the DMC proxy, the data management controller proxy. You're actually, instead of submitting your search to an individual shard, you are submitting your search to the proxy, which then scatters out to any shards in your database and gathers up the results, and then returns the single logical index. This one, by the way, is showing inverted indices, which is what's used for full text search. So we're saying that, doc1 has sun in the content. So here in the index, sun is showing doc1 and doc3. Now demo. So once again, this is going to be my my schema that I'm using. So session index on JSON, session colon starting, and this is the same one I showed you in a previous slide. Just want to reiterate that this is actually what I'm going to be using. I haven't added this to my database yet, so I'm going to be adding this first. And again, I just want to point out this is the syntax for getting all of the item IDs from the cart array. Moving back here, I'm going to be using the same database that I was using for the previous example. And so I need to add my session index. And then this is simply the same text that I showed you a moment ago on the slide, and enter. Okay means now I've got it. So if I want to find out, okay, so which sessions have been to redis.com, it would look like this: ft search session index at visited, and then redis.com. And here I'm saying all I really want to know is the visited. And so here they are. All right, so I've got the session ID because that's the document ID, and the visited. Let's say I want they visited example.com, but not example they visited Redis, but not example. Now, obviously, I could look down here in just this short 3 list and say, okay, that's going to take this one out. But of course, if you actually have user sessions going, you're going to need to do that search. You can't just look at it. And so sure enough, exactly as expected, I get 2 of those. Give me all the sessions that have MacBook in the cart. Here, by saying return 0, I'm saying I don't actually want any of the data. I just want the session IDs. And then I could use that session ID to get whatever additional data I wanted. Or I could say, hey, show me the carts that had the sessions that have a Ronco widget in the cart. Or show me the sessions that have either a MacBook or a Ronco widget. Those. Or maybe I want to know only the ones that have both. And that would be, okay, nobody's buying both a MacBook and a Ronco widget. I knew that in advance. I just wanted to show you the and syntax. Another example, I want to know everything. Give me all of the active sessions and sort by creation time, descending. And there are my sessions. The original 4 I started with and the one that I added in my JSON demo. But let's say what I'm actually interested in, though, is not just the creation time, but the last access time. And I want to sort by last access time. And I want it only for ever since this particular timestamp of interest. I could do that. I could also do search for location. So let's say I want to know all of the active sessions that are within 4 miles of Chicago's Union Station. That would be the syntax, and these are the 3. Maybe I want it even narrower. So within 1 mile of Union Station. That's this session. Again, the idea here being that all I really need is the session, and then I can do a JSON get for that session. And let's say, okay, I want to know the location of this one. So that would be, excuse me. I almost wrote it as a search criteria, but no, I'm not searching. I'm just getting $.location. And I say, okay, yes, that session is at Sears Tower. Now, those of you not from Chicago may be thinking, no, isn't that the longitude and latitude for Willis Tower? No, trust me, I'm from Chicago. It's Sears Tower, not Willis Tower. But anyway, that being the idea, once you found the session of interest, you can then use a plain JSON get to get the data of interest. And that's the end of my demo. One last thing before I turn this over to Julian. I mentioned briefly Redis gears in a couple of the caching patterns. I realize some of you, particularly those of you who are brand new to Redis, might not know what that's talking about. So let me just give you a quick, very quick primer on gears. Redis gears is a dynamic framework that enables you, the developers, to write and execute Python code that implements data flows in Redis. There are 2 options for the execution. It can either be batch, in which case you issue the run command, or event-based, in which case you issue the register command to register this script to be triggered by the events specified. Here are just some examples, deleting all keys whose value is smaller than 0, or write all the key names to a set, or listen for operations on keys and develop a list of key names, or listen for operations on a hash and map their data to a remote database. That's the one that's going to be useful for caching. Quickly, the anatomy of a function. Each function has a reader. There are 6 types of reader, but each function has only 1 reader. It can have multiple operations. All right, so this is the building blocks of your function. Defines the operations you want to be done. They're done in a pipeline fashion, meaning that data goes in, the first operation does its job, and then its output is the input for the next operation, whose output is the input for the next one, and so on. And then the action, what I was showing you before, you either run it now or you register it to run later. So to use the RGSync right behind example, it actually has 2 functions. Function A is reading the Redis database, looking for keys that match a particular trigger. And it synchronously grabs that information and puts it into a Redis stream. Function B is reading the Redis stream and then asynchronously transferring that information to the backend database. And so that would look something like this, where you've got the, you create the connection, initialize the connector, you specify the mapping. This one is showing hash, but the exact same idea works with mapping JSON path to column names. So here's my Redis data, and it corresponds to this in my relational database where I want to send this information. You know, Redis as a cache, sending information to the back end. And then the right behind object with the defined parameters defined in the documentation. So you know, which keys, what are the mappings, what are the connectors, what's the name of this function, what's the version of this function. Your functions can only have one active version at a time. So if you don't want to keep deleting the old functions and adding new ones, you need to update the version number. Then to execute that, in this case, we're saying that previous one, the caching object, obviously the caching function is going to be triggered. And so you write a function, let's say mygear.py, and then you register the function by going to the gears CLI and running mygear.py and specifying the requirements. So RG sync is the RG sync from here. You know, this is saying I need these things, so I need to tell it to get it. And then PyMySQL is just the basic Python client library for MySQL. I don't have an example of Redis gears, just wanted to give you a quick idea. And now I am going to turn it all over to Julian, who's got a very interesting demo for you.
Thank you, Tom. So let's talk about Redis Smart Cache. It will serve as an illustration of some of the concepts and technical details that Tom went through. So again, my name is Julian Ruel. I'm a principal field engineer at Redis, and this is Redis Smart Cache. So what is Redis Smart Cache? It is a JDBC proxy for read-through caching. And we'll see in the next slide what exactly that means. It does automatic SQL caching for your applications and microservices. So it's a no-code library that you can use. And also has some analytics built in, so you can visualize the expensive queries in your apps and microservices. So if we repeat what Tom was just saying about the different caching patterns and where we fit with Redis Smart Cache, if you look at this quadrant of caching patterns using Redis and Redis Enterprise, Tom just explained right behind. We talked about cache prefetching, read-through, cache aside. Redis Smart Cache is about the two top ones. It's cache aside and read-through in one single package. In cache aside, your service layer or your application interacts with a backend database and also with Redis. And it has to do the work of writing to the backend, reading from the backend, and copying that to the cache when necessary, right? So typically the cycle is the app will read from the backend, get the results, serialize that into the cache for later reuse. So the later reuse means the next time that same SQL query comes back, we can look into the cache if it's already there and save some bandwidth on the backend by using Redis. Read-through is very similar, except Redis takes care of reading from the database for you. So this is important here because in read-through, the service layer has to do less work compared to cache aside. So how does it tie to Redis Smart Cache? This is the architecture of Redis Smart Cache. You have your app or microservices that's currently using a relational database, the blue icon here. So your application reads and writes to that database, and we are focusing on the reads. And what we want to do is speed up some of these reads, typically a select statement in SQL. So for these select statements, we can use Redis to cache some of the recently seen results that we have for the same SQL queries. And what Redis Smart Cache does, it wraps around the backend JDBC driver that you have to automatically do that caching of SQL statement results. So the typical life cycle for Redis Smart Cache, it starts with an empty cache. And then when Redis Smart Cache starts to see queries coming that the application is running, it will cache some of them by taking the result set of a SQL query, putting it into the cache, so that the next time the same SQL query comes back, we will fetch it directly from the cache instead of going to the backend. So over time, as the cache builds, it gets warm, you will have more and more queries being served by Redis versus being served by the backend. So some of these queries that you can cache will automatically be cached by Redis Smart Cache, so that you have better performance and less burden on your backend, that it can be served for other purposes that may be more important for your business. So you can modernize your architecture without completely revamping the architecture. All right, let's go to the demo. So what I have here is a Spring Boot application. So it's, again, this is Java. This is all about JDBC and Redis Smart Cache. So the first prerequisite is having a Java application. So we have a Java application that interacts with a MySQL backend. And what we will see is as the demo starts, you will see performance being really bad. And then over the next few minutes, we'll see performance improve dramatically. So let me start this demo application, and we'll see the multiple components that are making up this demo instance. So you see there's multiple containers starting. This is all Docker Compose. And by the way, at the end of this presentation, I have a link to run this on your own environment. So let's see what we have running right now. You'll see that I have 4 containers. My backend is here, MySQL. I have my Redis server. In this case, we're using Redis Stack, our open source distribution with the modules that are necessary to run Redis Smart Cache. And we have our Spring Boot app running here. And then we also have Grafana, which will serve as the visualization for our demo to see what's happening in the demo app. So let's go to Grafana. Here, I will add Redis as a data source so we can see what's happening behind the scenes. And I will enter the Redis database information. There you go. And now I can import a dashboard that will show us how our application is performing. I will select the Redis data source for the time series to show up, and here we go. So you'll see that right now we have at the top of this dashboard the end-to-end throughput and latency for our application. You can see it's not very good. We have a query throughput of tens of operations per second, mean latency of hundreds of milliseconds with a P99 latency, basically the worst offenders being multiple seconds. So we have really bad performance because our MySQL backend is very, very slow. So these queries being run right now by the application are all served or mostly served by the backend. You can see the backend throughput pretty much reflects the query throughput, except now we're seeing some improvement. And that's because the cache has been warming up And now it's entering the fully warm phase where the application is having its queries being served by Redis and not by the backend. So here we go. We are in the fully warmed up phase of our application lifecycle. So all the requests at this moment are being served from the cache. So all the queries that are being run by this application have already been seen by Redis Smart Cache, and Redis Smart Cache has put the results in Redis. So Redis can serve these requests in sub-millisecond response time, as you can see right now. So our application throughput is now almost 40,000 operations per second. That exact same SQL is being run in much less time. The mean latency is 0.2 milliseconds, and the worst latency is 0.4 milliseconds. We see how dramatically we can improve an application response time by putting Redis Smart Cache inside the app. And to do that, we just need to add a JDBC driver from Redis Smart Cache, configure it to talk to the backend like you would do with your normal application, and also connect to Redis. So it's just a configuration change for your existing application. There's no code change. And that translates into caching automatically being done or transparently being done for the application. And we can see right now we are in our cruising mode for the app. The caveat is that there's a time to live for the entries being put into the cache by Redis Smart Cache. So when we saw that the cache was fully warm, at some point, the entries will be evicted from the cache. This is meant to be this way. It's what we want for a cache to be effective. We want to invalidate the results at some point so that we are not returning results that are days old. We want to, at some point, recycle these entries so that we get fresher results. And this is all configurable in Redis Smart Cache. So you can set rules that will tell Redis Smart Cache how long you want to keep these results for specific SQL queries or for specific tables in your backend. So what we'll see by default in this demo application, the time to live is 5 minutes. So after, in a couple of minutes, we'll see some performance degradation. That's because the entries in the cache will be evicted, and Redis Smart Cache will have to go back to the backend database to actually get the results. Here we go. So now we are seeing performance degradation going back to what we saw initially when the cache was cold, and that's meant to be this way. This is because the entries have been evicted, and now we're starting the cycle again where we are warming up the cache again to get the fresher data from the backend. You'll see latency went back to seconds for the worst P99 latency, and then the mean latency is back to half a second, and probably will increase a little bit more before we enter the cache being fully warm again, in which case we'll see better performance like we saw initially. All right, let's go back to the presentation. So when can you use Redis Smart Cache? So the first requirement is that you have a Java application or microservice. And you see some patterns where your queries are slow and you have repeated queries that are slow. In this case, you can use Redis Smart Cache to cache some of these results that you can live with the results not being exactly the freshest. So typically, if you have reference data in your backend database, customer information, product information that doesn't change very often, then you can use Redis Smart Cache to cache these entries so that your SQL statements will be that make use of these less transactional data can be cached and served from Redis instead of from the backend. So these three requirements: you have a Java app or microservice executing slow queries repeatedly, and you have some tolerance for stale results, right? So, and this is again configurable in Redis Smart Cache. You can configure how stale the results should be. So you have a rule that says this table should be cached for 2 hours, this other table should be cached for 5 minutes. This exact SQL query should be cached for 3 minutes, etc., etc. All these rules can be put into Redis Smart Cache, and you have a tool, a CLI tool that you can use to interact with the data that's gathered by the Redis Smart Cache in order to activate or deactivate some rules that are dynamically executed by Redis Smart Cache. If you want to learn more and try this for yourself, you can go to this URL, bit.ly/smart-cache, and you'll be able to give it a spin like I did during this demo. Here you go, poll question number 4. Maybe Janelle, you want to take this over?
Yes, absolutely, Julian. And thank you all for joining us. I will launch poll question 4, and you will see that very shortly on your screen. But we would like to know if you would be interested in attending any other of our virtual workshops. We have virtual workshops on Redis Enterprise, on admin operations, as well as an upcoming Redis Enterprise search applications virtual workshop on May 18th. I did type into our chat for everyone to see all of the upcoming programs that we have going on, and I'll go through some of those momentarily. But definitely, we would love to see you at future virtual workshops. And we have a full portfolio of topics run with our amazing professional services team and our solutions architect team. So we would welcome seeing you at another future workshop. So excellent. Thank you all for that response. And I will end our poll now. And our final poll question is, we have Redis individuals and teammates all across the globe, and we would absolutely love to have a follow-up conversation with each of you. We have Redis individuals across all continents and countries. We realize people are joining us all across the globe, and we have teammates who can follow up with you and would welcome having a conversation. So please do let us know how we can answer your questions and work together with you in the future. We are always happy to have a chat and make sure that you are all set on your Redis journey. We are always here to help you along the way. So give everyone a moment to respond to that poll. And then I'd like to go through some upcoming programs that we have. So Julian, if you would like to go to the next slide, that would be great. So we do have our Redis Days virtual program coming up on May 24th. This will be an amazing virtual session with keynotes from Tim Hall, our Chief Product Officer. We will have amazing customer presentations and a presentation on generative AI and LLMs as well. So definitely that will be just an amazing session for you all to tune into wherever you are. So we would love to have you register and join us for that session. And you can do so by scanning the QR code or visiting our redis.com website. So we would welcome having you at that upcoming Redis Days virtual session. And then next slide, we also have coming up, as I mentioned, we are doing an in-person as well as a virtual workshop on search. So our virtual search workshop will be on May 18th, but we will be running a series of in-person search workshops across the United States. So you can see all of the different cities that we will be in: Denver, San Jose, Chicago, Seattle, New York, Dallas, Boston, LA, and Austin. So if you or your teams are in any of those cities, we would welcome having you join us in person for our real-time search workshop series. And as I mentioned, we are having a Redis search applications virtual workshop next week on May 18th. So a link is in the chat. If that is of interest, definitely you can also find that on our redis.com website under events and webinars. So take a look at all of that, but we are deeply appreciative of your time today. Thank you, Julian and Tom, for the excellent presentation. And we will open it up to questions. So everyone, please do ask any questions that you have. You may type those into the Q&A, or you also may type those into chat, whatever works best for you. We would love to answer your questions, so please feel free to type them. But thank you all for joining us. We are always here to help you along your Redis journey and have a ton of resources both on our redis.com site, our Redis University site. So check out all of that, and we'll just pause to see if we have any questions. And I might also say, Tom or Julian, if you have any questions or final comments as well for our audience, that would be great. If you have any closing comments or thoughts.
Not for me. I've used up my talking allowance for the day.
Got it. Well, that's fair, Tom, and Julian as well then. Well, we are just extremely grateful of you all spending your time with us today to learn and grow with Redis. And we will definitely look forward to seeing you at a future session. So thank you all for joining us today, and have a wonderful rest of your day, afternoon, evening, or morning, wherever you all might be, and enjoy the remainder of the week. Thank you, everyone.